In this video, we're going to recap the absolute basics of informal set theory. So we will talk about the definition of a set, about members or elements of a set, about what it means for one set to be a subset of another set, and about what it means for two sets to be equal. So let's begin with the definition. A set is defined to be a collection of mathematical objects. And the way we tend to notate these collections is by using curly brackets like this. So this expression I've just underlined denotes the collection of mathematical objects 1, 2, and 3. So sets are what we use for reasoning about unordered collection of objects, ignoring repetition. So let me try and say what I mean by unordered and ignoring repetition. When we say unordered, what we mean is that if we take these two sets, for example, so 1, 2, and 2, 1, those things are to be regarded as equal sets, so literally equal. And again, what we mean by ignoring repetition is that if I take a set such as this, then this is equal to the set which just contains the element 1. So if we do care for some reason about the order of some elements or about repetition, we have other mathematical structures for dealing with those. For example, sequences. But when we talk about sets, order and repetition don't matter. So we're going to give a slightly more formal definition of when two sets are equal in a couple of slides' time, which will make it clear precisely where this property comes from. So we have some special notation for the things which make up a set. We have this symbol here to mean that an element, a thing X is an element of the set A, and then we use the same symbol crossed out to mean that an element, a thing X is not an element of a set A. So as an example here, if I take the set 1, 2, as we've just seen, one of the things in that set is 1, so we write this to mean that 1 is an element of this set. On the other hand, 3 is not an element of that set, which we write like this, the same symbol crossed out. Now there's a special set which we have some special notation for, the empty set, which we write like this, kind of 0 crossed out, is the set whose defining property is that it doesn't have any elements at all. So no matter what A is not an element of the empty set. Now we don't restrict ourselves in what the elements of a set can be. They don't all have to have the same type. They don't all have to be numbers. So, for example, matrices, vectors, functions, sets themselves can be elements of a set. So here is an example of a set X, where the elements are the empty set, the number 1, the set containing the number 2, and the set containing the number 3. Anything is possible. We allow any kind of mathematical thing as an element of a set. All right, let's now move on and talk about some further definitions. We say that one set X is a subset of a set Y when every element of X is also an element of Y. And we say that two sets X and Y are equal. We write that using the usual equality sign here, if and only if X is a subset of Y and Y is a subset of X. So what that means is the things which are elements of X are exactly the same as the things which are elements of Y. And finally, we say that a set X is a proper subset of an XY, of a set Y, which we write like this, if X is a subset of Y but it's not equal to Y. So that means that every element of X is also an element of Y, but there's something in Y which is not in X. Okay, let's explore a few examples of this. So here we have an example of a subset. The set containing 0 is a subset of the set containing 0 and 1, because every element in here is also an element in here. On the other hand, this set is not a subset of this set. The reason is there's an element in here which is not, and there's an element in this first set which is not an element of the second set. Namely, 2 is an element of the first set and it's not an element of the second set. So as you can see, we use the subset symbol crossed out to mean that something is not a subset of something else. Finally, let's just take another look at that definition of when two sets are equal. So two sets are equal if something is an element of the first set, if and only if it's an element of the second set. And you can see that that makes these two sets here, so this set and this set, it makes those two sets equal. So the only things which can answer yes to the question, are you an element of the set on the left here, are the numbers 1 and 2. And the only things which can answer the question, answer yes to the question, are you an element of this second set here, are the numbers 1 and 2. So the elements of this first set and the elements of the second set are the same. And that means these two things are equal by definition. So that's the way in which our definition of two sets being equal captures the idea I had on our first slide that sets ignore repetition and ignore order. Okay, a final comment about sets and subsets is that for any set X, the empty set is a subset of X. So why is that true? That seems like a strange property. Let's think why this is true. Well, one reason is that if you look at the definition of subset up here, well, the definition of subset holds here because every element of the empty set is also an element of your set X, no matter what X is, because there aren't any elements in the empty set. So let's put this another way. I mean, if you think a set A is not a subset of B, so if you think this is not true, well, what you've got to do is produce an element of A which is not an element of B. So if this is true, then there exists an element little a and big A with little a not in B. Okay, but you can't find an element of the empty set which is not in X because there are no elements of the empty set at all. Okay, so you just have to accept that according to our definition, the empty set is a subset of every single other set X. Okay, but don't get mixed up between subsets and elements. It's not true that the empty set is an element of every set X. It's just true that it's a subset of every set X. So for example, here is a set which does not have the empty set as a member, right? The only elements of this set here are the number 1, and the empty set is not the number 1, so it's not in here. All right, moving on. We have one final bit of notation for constructing sets, which is called set builder notation. And on this slide, we're going to describe set builder notation. So let's suppose you've got a set X and a property which applies to the elements of that set. So by a property, I just mean something which might be true or which might be false. But for every element of the set, either it's true or it's false. Then we use this bit of notation to mean the set of all of the elements in the set capital X for which that property is true. So this is easier to understand if we look at a specific example here. So let's take our set capital X to be the set of all integers, which we often write with this blackboard bold Z thing here. And by an integer, I mean a positive or negative whole number. So for example, -2, -1, 0, 1, 2, and so on. And we're going to take our property, P of little x, to be the property X is even. Now, that's a property in the sense that I mentioned just now. Every integer X is either, for every integer little x, this property is either true or false. So we can use our set builder notation here to form this set X in Z, P of X, and that means all the integers X which are even. So in other words, all the even integers that consist of things like -4, -2, 0, 2, 4, 6, 8, 10, -1000, and so on. Okay, so this set builder notation is very, very common. You'll see it used all the time, so it's important that we describe it here. Alright, so last thing for this video, let's just look at an example of proving two sets which are defined using this set builder notation, proving that these two sets are equal. So here is the first set, A, that's the set of all x in z, so the set of all integers x, with the property that x is odd. And B here is the set of all integers x with the property x plus 2 is odd. Now I claim that A and B are equal, they're the same set. And so let's think, I mean maybe this is obvious to you, but we're going to try and think very carefully about why this is true. And we're going to use the definition of equality of sets which we described on the last slide. And that definition of when two sets were equal was that two sets A and B were equal if and only if A was a subset of B and B was a subset of A. So it happens all the time that in mathematics that you want to prove that two sets are equal, and one way which you can always use to do that is to prove these two subset relations, so that you prove A is a subset of B and you prove B is a subset of A. So let's try and do this in our example. So the first thing we need to prove is that our set A is a subset of B. So to do that, we have to pick any element in A and prove that it's also an element of B. So let's do this. Let little a be an element of A. And what I've got to do first of all is show that it's also an element of B. But that's easy, right? I mean, if little a is in big A, well then A is an odd integer. Okay, if A is an odd integer, then A plus 2 is also an odd integer, right? If you add an odd number to an even number, you get an odd number. So A plus 2 is also an odd integer. All right, well, does this A fulfill the criteria to be in B? Yes, it does. It's an integer, and we've just seen that if you take this number A and you add 2, you get an odd integer. So it fulfills this property. So A is in B. All right, we took any element of A, we proved it was in B. So what we've done is we've shown that A is a subset of B. All right, if you want to complete this proof, I'm not going to do it, but if you want to do it, then you have to take any element of B and prove that that element is also an element of A. And when you've done that, you'd have shown that A is a subset of B. Well, actually, I did that. But then you'll have shown that B is a subset of A. And so, if A is a subset of B and B is a subset of A, then A equals B. And that's the standard way that we prove two sets are equal, to do both of these subset relations. Okay, we're done. What you should do now is scroll down the page a little bit, find my stack quiz about set membership and subsets, and do that quiz. But that is it for this video.